this fifth edition of the Open Doctoral Lecture, co-organized by the Université Côte d'Azur in Nice, by the CNRS network GE2AMI, by the University Mohammed VI in Morocco, and by the University Sadi Ayad, also in Morocco, Marrakech. It's fifth edition. Yep. So we have the great pleasure for this week and for this new edition to welcome Professor Zuazua, Professor Enrique Zuazua. The title of the lectures is Introduction to Optimal Control and Machine Learning. So let me say a few words about the bio of Professor Zuazua. So Professor Zuazua has been holding a chair since 2019 at the University of Erlangen in Germany. And the chair is in dynamics, control, machine learning, and numerics. At the same time, Professor Zuazua has some appointments in Spain, Bilbao, and Madrid. Professor Zuazua got his PhD at the University of Basque Country in Spain and Université Pierre and Marie Curie in Paris in 1987 and 1988. Since that time, he has published many articles, more than 300 articles. He has supervised more than 30 PhD students, and his field is in general applied mathematics, and this includes PDEs, partial differential equations, system control, numerical analysis, and machine learning. He is the co-editor-in-chief of journals in mathematics, so mathematical control and related fields, advances in continuous and discrete models, and he is also the member of several top journals, member of the editorial committee of several top journals in mathematics. He has received several awards in his career. This includes recently the Reid Prize in 2022 and some European grants, ERC grants in 2010, 2016, and more recently in 2022. So we are very happy to have him for this lecture. So please, Professor Zuazua, welcome again.
Thank you, Francois. Merci. Thank you, Abdou. I'm very pleased to be here with you in this fifth edition. I also thank all the partners that are organizing this event, both in France and in Morocco. I have been participating in this CNRS network since it started under the leadership of first Gilles Lebeau and then later Francois, maybe ongoing now for 15 years or so. So yeah, and Morocco is a broader country that I often have the pleasure of visiting. So I have followed the career of many of the now well-established researchers, young researchers at that time in Morocco, and I admire a lot how applied mathematics is evolving there in the country. This applies also to the other broader countries in Maghreb. So, and Nice is a great place. Maybe it would have been nicer for me to be, facing the ocean, facing the sea, to lecture this series from a balcony. But this will be done next time. I'm here in Erlangen, and today the weather is sunny, something that here we celebrate, especially because this doesn't occur so often. Very good. So now the first lecture, I wanted to make some historical comments. Well, people often in mathematics think, why don't you get directly into the, the definitions and the theorems and the technical content? So I think when talking about these topics, control, machine learning, optimal control, it is worth to have a panoramic look, right? And try to think a bit historically. Of course, history is non-linear, right? So actually, even the classification of topics, of fields, is not so easy to do, right? And you will see that during the lectures to a large extent, right? So what control is, or control, optimization, calculus of variation, optimal design, even machine learning and artificial intelligence are all broader topics that share to a large extent the same goals and also the same kind of mathematics. And the difference comes very often just by the way we as scientists decide to model the practical or applied challenges we are facing. In the case of control, this is certainly a very interdisciplinary topic that has been developed in cooperation with engineers. So you will see often, in the subject classification, keywords such as automatics, automatique in France, cybernetics, control engineering, mathematical control, control sciences, right? So this really means that the topic, the field has been developed in close cooperation between engineers, computer scientists, and mathematicians in particular, right? Simply because in every real process we are handling, it's not simply sufficient to model it and understand how solutions behave and do maybe PD analysis or OD analysis about existence, uniqueness, qualitative behavior, or numerical approximation. But very often, applications also require that we understand how to manipulate the system, how to gear the system, how to drive the system. And for this, normally we have both sensors and actuators, and this opens a whole new array of mathematical questions that I will try to present here, right? As I said, oftentimes the same problem can be handled from a slightly different perspective, and this is why there are other, sister areas such as optimization, calculus of variation, optimal transport, right, that also arise, combining similar ingredients but with a slightly different mathematical flavor. Okay, so things started, with the origin of our civilization when, people like Protagoras de Abdera said, man is the measure of all things, right? So humans, we are the measure of all things. We are put in this huge universe at our scale. So, our size in between 1 and 2 meters, roughly speaking, right? So we understand what a meter is. And then out of this meter, we can, go down and scale down centimeters, millimeters, or go up, right? And then measure in terms of kilometers. But we often, very soon lose perspective, right? So this is why, when we are talking about large distances, well, we still understand that maybe there are, I don't know, like 10,000 kilometers from Paris to Beijing, right? So these are sizes that we are still used to. But as soon as we are dealing with the challenges of the universe and we start measuring in terms of light years, we completely lose track. The same happens when we are scaling down, right? And we get into the nano scale, where things not only are very little, but actually change in nature, right? So the Pythagoreans took seriously this idea of Protagoras, and then they developed a school whose main aim was to measure the universe, right? So they wanted to know what is the distance to the moon, right? Right, or how understand why the sequence of day and nights, what was the length of a day, right? How to understand distances in Earth. Their goal was to measure everything using numbers, and at that time for them the numbers were just integer numbers, 7, 13, 49, and rational numbers, 3/4, 5/6. But it was themselves, within the school, they soon discovered that their goal was impossible. They actually, one of the school members, right? There are several versions about what happened to this poor guy of the school, this young fellow that came one day in the morning to the school and said, well, I have discovered that the whole goal of the school is impossible because, in the hypothenusa of a triangle of sides 1. You know, the length is the square root of 2, and the square root of 2 is not a rational number. There are several versions about what happened to this young fellow. One of them says that in a boat trip, the guy disappeared, right? But still, you know, the truth is that finally Pythagoreans understood that this being true, it had to be accepted. But, you know, this didn't mean that their program was not feasible. This simply meant that they had to enrich the basis of numbers they were using, the class of numbers they were using, integer, rational, to add the irrational numbers. Later, of course, came the imaginary numbers, and this keeps on going, right? So this is precisely the role of mathematicians. So to build models that are consistent, but rich enough in order to describe nature. And then we have always also to keep in mind that although we as mathematicians, we are used to take, you know, the equation under consideration as the real truth, this is, you know, always necessarily just an approximation to the reality. The universe will always be much more complex than any equation we can aim, right? Well, despite of this, mathematics has been greatly successful. Civilization after civilization, we got to this point where, you know, we live in a society of information, extremely technological, full of data, interconnected, and this allows us, for instance, to run this course online very, very efficiently with a very good quality of image and sound, right? But the challenge has always been the understanding of nature, as the Pythagoreans already, you know, adopted as their motto, right? There are actually very relevant sentences said by the most celebrated scientists. For instance, this sentence by Feynman, who was awarded the Nobel Prize because of his contributions to nanosciences, right? And he said something like, our imagination is stretched to the utmost, not as in fiction, to imagine things that which are, you know, don't exist, but simply to understand nature. So we don't need to get into very, you know, sophisticated new universe to get involved in very hard mathematics. Just the understanding of motion of birds or the behavior of people is already complex enough and requires and justifies all the mathematics we have developed. Actually, mathematics together with language, right, are probably the two main constructions of humankind, right? So if we have to distinguish a human from another living animal, probably our ability to develop mathematics and to communicate in many, many different languages is probably that, you know, what makes us different from all other animals. Actually, in the old Roman La Planète des Singes, as you know, at a given time, you know, the human is trapped by the singe, and then he has to show its own intelligence, right? And then in order to do it, finally, what the man does is to draw, you know, with a stick in sand, the Pythagorean theorem, right? So as a proof of the fact that the human was a peaceful and intelligent animal, right? So you want to show that you are really human, the best thing you can do is to show, right, that you are able to understand, you know, Pythagorean theorem. And science and mathematics have been ongoing, you know, tackling the challenges of nature. There are many, many very interesting anecdotes. This one, for instance, Pierre Fermat was, as you know, sitting in Paris and trying to, you know, tackle some of the most curious problems in physics and mathematics. He, for instance, tried to prove the Snell law about the refraction of light, right? So the, you know, a phenomena that we have all observed just by inserting a stick into water, and we have this perception that the stick is folding. Of course, the stick doesn't fold, it's just a visual and optical effect, right? So Pierre Fermat formulated this problem, but he could not solve it. And in a letter to, I don't remember to whom, one of the Bernoullis or so, he recognized that he was not able to solve the problem. But of course, you know, he was not a very modest person. So the way he indicated to the interlocutor that he was not able to solve the problem was by saying, this problem is not one of the easiest, right? So normally then I recommend to students when they are going to an oral exam and then the teacher asks about a question that they don't have any clue, right? Maybe this is an elegant way of getting around this complicated situation. You can always say, oh, professor, this problem is not one of the easiest, right? Yeah. So the same Fermat, of course, is the one that made this note in the margin of the book indicating that he had found a solution to the classical Fermat problem, but there was not room in the margin of the book for him to write the proof. Now you can decide yourself whether Fermat had the proof or not. You know that it took us more than 300 years to do it. And also when you look to the proof of the Snell law nowadays, this is just a calculus 1 exercise. You just need to compute the critical point of a function in one variable, right? So given that Fermat was not able to solve that problem, probably he was not even either able to have a complete proof of his own conjecture. Still, his contribution was gorgeous because this kept all the mathematical community busy for more than 300 years, right? By the way, this passage, of course, belongs nowadays to the history of mathematics. Recently, I was visiting Sorbonne University, and in the Saint Michel metro station, I have seen written, or maybe it was in Jussieu, I don't remember. In the metro station, I read on the wall. Some young students certainly wrote in the wall a note indicating, oh, I have another proof of the Fermat theorem, but the metro is coming and I don't have time to write it down, right? Okay, so then the Snell law, this is described in this beautiful book by Ernst Heider and Vanner, Analysis by its History, that I always recommend to all math professionals. So where calculus analysis is described not according to the classical presentation of epsilon delta continuity, derivatives, and so on, but rather following the historical order. And there they describe this passage about Fermat trying to solve Snell's law. And there you also can find the proof that, as I said, is just a calculus 1 exercise that at that time, of course, Fermat didn't know how to deal with, because concepts like derivative, critical point were not mature at that time. Things evolved, back in the late 18th century, for instance. Gaspard Monge, also in Paris, right? So there is a street near the Botanical Garden, near Sorbonne, dedicated to him. He wrote this seminal paper about the optimal transportation of material goods from one place to another, right? So, each of us had the opportunity sometime in the past to move from one apartment to the other. And you know that this is not necessarily easy, right? It's not like taking a bag, putting your belongings and moving there. We always accumulate more belongings than we think. So the problem of optimal planning, the transport, whether you want to do it by bike, by car, or whether you need a professional company coming, with a big truck to support you in this moving, is not a trivial issue. This was the problem that Gaspard Monge, was developing in his celebrated paper Sur la théorie des déblais et des remblais, right? So later, Kantorovich got the Nobel Prize in economics because he understood how to expand the theory of Monge by relaxation to the context of finances and economical growth, right? The idea being that when you are transporting goods, right? When you are transporting a chair, you cannot cut the chair into pieces, right? But when you are transporting wealth, you can do that, right? So these are measures that you can decompose, transport by pieces, and reallocate. And this is, for instance, what we do with our tax system. in which we transport wealth from, one class of individuals to another one through the tax system. We all pay taxes, say 25%, university professor, we pay, 25% taxes. And this money that the government collects is then used in order to allocate fellowships, unemployment aids, pay pensions, and so on. Okay, and this field of optimal transport, which is also, of course, very much related to optimization and control, right, has been ongoing, and you still see regularly how Nobel Prizes in economics are allocated to people doing contributions in these areas. For instance, Alvin Roth is very well known in Bilbao, where I was born, in Basque Country. Back in 2012, he got the Nobel Prize in economics for his contribution to optimal transport. And two applications are mentioned in his Nobel nomination. One of them is his contribution to the optimal routing of the school buses in Manhattan, in New York. As you can imagine, there are a few buses, right, going around from every point, every corner, every street to every school in town. And then the optimal routing of these buses is something relevant, right? Because you don't want your child to spend too much time on the bus. Also, of course, it contributes to, a more rational traffic and to less consumption of gas. And the other contribution of Alvin Roth was to design also the optimal routing of the donation of organs in the US, right? So, of course, if someone is donating a heart in California, and this heart has to be transplanted to someone that is waiting in Miami, you want this heart to be transported optimally, in optimal time, right? In Bilbao, we know him because when we built the new stadium of the San Mamés, of the Athletic de Bilbao soccer team, the new stadium was built more or less in the same location, a bit wider, oriented differently to have better lighting, and so on. Then the issue was how to transport each of the 40,000 members of the athletic team from their seat in the old stadium to the seat in the new stadium. Well, these are the kind of problems that look very simple. You just take one of them and then put it in a similar seat, and then you go to the second and you go to the third. But when you have to do that optimally for 40,000 individuals, or very opinionated about the quality of his seats and the fact that they don't want to get anything worse, right? This is something extremely complicated. So Alvin Roth was there to support the team in organizing this through, say, advanced computer programs. So computers have been, of course, one of the key successes of mathematicians. So to understand, accept that this original goal of the Pythagoreans, despite or because of the huge evolution of the mathematics we were able to, to create, right, was requiring also of new tools in order to tackle complexity and the course of dimensionality. And this is how, from the original Pascaline of Blaise Pascal, things evolve very rapidly into modern computers, or, now even, cell phones that are able to contribute significantly to our success on tackling complex issues. Knowledge is being accelerated. We can feel that every day, right? So I still recall as a student in Paris 6, 40 years back, when the first Macintosh computer came, right? Until then, computers were in a special room where only some engineers were working. And then suddenly, with the emergence of this, at that time, they were considered to be portable, although they were weighing, 10 kilos, and they had the size of a small fridge, but they were still, much smaller and friendly to be used than the classical computers. So 40 years back, the first computer came to our offices. Now we have computers in every home. Later, we got the cell phones. 25 years ago, we discovered, Google for searching. And nowadays, we have ChatGPT. Things are accelerating very, very fast. And these new technologies are getting to anyone, right? Of course, there is a price to pay, and the price of globalization, one of the prices of globalization is that multiculturalism is shrinking. Many minority languages are disappearing, right? So, you know, it is estimated that every 2 weeks or so, one language is disappearing in the planet. But mathematicians, we are lucky because there is a unique language for mathematics, and this one is getting reinforced, right? So we see that every day, you know, mathematics is playing an ever more relevant role in the whole ensemble of the rich tree of sciences, in which we see new branches appearing regularly, right? So in particular, machine learning, artificial intelligence is a quite brand new branch that is transforming our way of living, because in particular nowadays everyone uses tools like large language models, ChatGPT, and so on for, you know, for writing a letter or improving a text already written, or to getting, you know, information about some specific topic in a much more agile manner than ourselves clicking in Google looking for the keywords, right? So now ChatGPT does the work. I just asked to ChatGPT, can you explain me, you know, the difference between traumatology and physiotherapy? And then ChatGPT will write a paragraph for me explaining what the difference between traumatology and physiotherapy is, right? I don't need to go to Google and then click first traumatology and then go to Google again and click, you know, second physiotherapy, go through the two paragraphs and then make the comparison myself. ChatGPT is doing that automatically for me, and this is a great advance. So this is a new branch that emerged, you know, out of the tree of sciences that is always growing, but mathematics remains always in the very roots, in the epicenter, right, of this tree, and as you will see, is also contributing significantly to the development of this new age of machine learning and artificial intelligence. And this is why probably nowadays mathematics is one of the diplomas that is more demanded in the job market. Mathematics, mathematical sciences, engineering mathematics, data sciences, these are probably some of the diplomas that you know, are more successful nowadays in the job market. And this is really a surprise in some sense, right? So when I started my university studies, people will even ask me, so why are you doing mathematics? Why don't you study engineering? If you study mathematics, the best you can be is a teacher in a high school, right? So a mathematician is, you know, is someone that is condemned to be, you know, very, very limited in the search of a job, right? At that time, that was the state of mind. And now you see that it's totally the opposite. And I think there is a reason for this. And the reason for this is that Pythagoreans already did the job, right? So Pythagoreans said, listen, if we want to understand the complexity of the universe, we need to use mathematics. And this is why the society we have built is, you know, based fundamentally on the use of mathematics. And the more this society evolves, the more mathematics, you know, will be needed. And this is why I think probably this is one of the reasons why mathematics will be ever more and more demanded, right? When things get more complex in finances, in political decision making, in medicine, in the management of resources, you will always need more and more mathematics, and therefore more and more mathematicians. And this is why education is probably, you know, we are, yesterday I was reading an article about the University of Zurich. The University of Zurich decided to abandon these international rankings, right? And the reason for that was that, you know, when universities enroll these international rankings, then the course is, you know, the challenge is to see, oh, which university publishes more papers, has more citations to be high on rankings. And their message was, and by doing this, somehow we are forgetting that our main role is to educate the new generation of citizens, right? And in particular for us, our main role is to educate the new generation of mathematicians that then will do something that we don't even imagine, right? I'm sure, for instance, when I was teaching, I was learning my master courses in Sorbonne, right? I was taking courses with Brecis and Sierlet and Glowinski in classical PDs and numerical analysis and so on. None of them was thinking at that time that maybe some of the most hottest topics nowadays will be related to issues such as randomness, uncertainty, machine learning, and so on, right? But but this is the nature of the evolution of the society of the sciences. This doesn't really matter. If you have educated people properly, they will be ready to, face these new challenges. And this is our role. And this is also the aim of this course, right? So I try to share with you what I have, come to know, and hoping that you will make a good use of this in order to tackle topics that in the future, I cannot even anticipate which ones they will be. But I'm sure you will do that successfully. So following this very, idea of the Pythagoreans of modeling nature through numbers, we have got very far. We have developed, for instance, aeronautics inspired on the flight of birds. Of course, we cannot fly as birds, but we can build airplanes that are able to transport successfully long distances, hundreds of people. And this is, something really amazing if you think, right? So you really, when you observe how far technology brought us, you really realize that there is something unique on the humankind, right? But of course, you can discover mathematics everywhere. Fractals, for instance, are discovered in nature and are also used in art. You just go to Alhambra in Granada and you can, observe the beauty of these fractal structures used, in the Arabic constructions, before 15th century. And something that characterizes mathematics and that is extremely relevant in these lectures, because as you will see, ideas from different disciplines are mixed up in a way that you cannot really unmix, right? Is the unity of mathematics. The unity of mathematics, the universality of mathematics is what allows us to use the tools that were, for instance, developed, the same Navier-Stokes and Euler equations that were developed to tackle challenges such as aeronautics, right? To deal with, for instance, hematology, the cardiovascular system, the flow of blood in human arteries, right? Because if there are three important fluids in nature, the three of them are certainly blood, air, and water, right? So without blood, air, and water, we could not survive. Of course, the fourth most important fluid is coffee, right? Because as Erdős indicated, a mathematician is a machine that transforms coffee into theorems, right? So, but, before coffee, there is still, blood, air, and water that is needed in order to, survive. And the beauty of mathematics is that the same equations, the same numerical algorithms, the same control tools that you use in order to regulate an airplane, air, or a river, water, you can also employ to understand the cardiovascular system. Very often we can do it through deterministic rules, like the classical gradient descent algorithm, when you are minimizing a functional in optimization or in the calculus of variation. But sometimes we face such a level of complexity, like in this kind of fractal surface here, in which it's very hard to say whether you are sitting in a red point or in a blue point. In such an irregular landscape, you cannot even compute gradients. So when this happens, you can still, use Monte Carlo like algorithms, principle based on randomness to compute, right? So in this way, mathematicians, we have been always able to turn problems around. So what in principle was an impossible problem, like minimizing functionals in rough surfaces like this, because there is not a clear notion of gradient and orientation, right? Will turn it into, new methodologies that empower us to tackle more complex problems. For instance, all those related to stochastic gradient descent, right? And then sometimes you also wonder, well, there are many things that have been done through mathematics. For instance, in aeronautics, there is a lot of mathematics. Then in some other cases, you face, for instance, in architecture, very beautiful constructions like, the Gaudi buildings in Barcelona or the Guggenheim Museum here in Bilbao. And in principle, this was done by architects, right? But when you look at this as a mathematician, you wonder, I mean, is it true that there is no mathematics there? There is certainly plenty of geometry and optimal shape design there, right? So you see that there is people also that, not being mathematician, have some intrinsic mathematical understanding, right? Maybe without requiring mathematical education and the rigor of the mathematical, say, logics and formulas, but they have somehow the maths built in their brains, right? That which allows them to generate such beautiful geometries without, in principle, using the tools of mathematics. And maths not only allows you to do, but also to undo. The same, the classical theorem of the inverse function theorem or the implicit function theorem, that when we look, we learn them for the first time in a school, in university, they look a bit odd. So why are we doing this? Why do we need to invert? Well, we need to invert because very often in our lives we need to go backwards, right, to better understand things. This is something has occurred in the climate sciences, right? So we had to work hard, right, to understand global change, going back to the origins, to really realize and discover that to a large extent the action of man was inducing this global change, so to be able to take the measures that will compensate, at least partially, this phenomena. And the same maths that are used to, understand, global change can also be employed to understand animal behavior, right? So let me show you now here a very simple application of control theory, right? In which 4 dogs are herding a flock of sheep. So you see here in blue 4 dogs moving, right? And this is inducing the motion of all these sheep here that are traveling along these characteristic lines, right? So this is a classical problem in which we are tackling animal behavior, right? But from a control perspective. Why a control perspective? Because in this case, there is a state, is the position of all these sheep that, as you see, have been gathered together, right, around this point at the center of this crowd, right? And this has been so because of the intelligence action of these dogs that were moving strategically, inducing, this motion on the sheep by repulsion, right? I mean, this is an apparently simple application in control theory, yet if you do it mathematically, this is quite challenging, right? And again, so you wonder, I mean, how shepherds know how to herd, crowds of sheep. How shepherds do it? They didn't learn mathematics. They didn't learn control theory. We could do this, but in order to do this, we have to write a very complicated system of ordinary differential equations describing the interactions between dogs and sheep, and then formulate a control problem. And this control problem, of course, is non-linear, is non-convex, is high-dimensional. We cannot solve it analytically. The only thing we could do is to launch some stochastic or, stochastic gradient descent method in order to make the problem accessible, right? And then plot what the optimal or quasi-optimal solutions were. So we were able to do this because we knew all these tools of advanced applied mathematics. But somehow the shepherd, right, who is a professional in this business, is able to solve this just following his own intuition, right? So you see that somehow, mathematics is also a tool that many people use, even though they are not trained as professional mathematicians in a way or another. They are able to find this optimal mathematical solution without going through the intricate, paths of rigorous mathematics. Okay, and nowadays mathematics is everywhere. So there is mathematics in soccer, of course. Now the soccer market that is so relevant, in particular in countries like France, Spain, and Morocco. This is probably activity number one, right? So and the challenge is so huge that you even need to use mathematics in order to allocate a number of value to every player that will go into the market, right? So I know, for instance, Real Madrid has been trying to hire Mbappe since I don't know how many years, and now say probably this summer this is going to happen, right? And because of this, in our universities, we try to train people, right, by teaching them the foundations of mathematics, but also keeping always an eye on the new applications, the new developments, so that these efforts, although the mathematics remain the same, somehow the orientation of these efforts is pointing towards more contemporary applications. So, math is always often considered to be kind of a sad, topic, quite complicated and convoluted. And this is somehow true because the math book is depressed because it's full of problems, right? But there is also a lot of humor, and this is oftentimes also observed in the movies that more and more adopt very often mathematical topics. As Sofia Kovalevskaya said, the poet must see what the others don't see, and the mathematician has to do the same. So in some sense, we mathematicians are, the poets of science. Concerning control, very much in parallel to the developments of Protagoras, the Abdera, and the Pythagoreans, Aristotle started somehow advertise the need of the science of control. So he was the one to say that in order to make humans free, we needed to develop machines that will do the work of humans, right? So if we can be, talking here like this without paying attention, focusing only in mathematics, is because we don't need to pay attention to light, to internet, to the functioning of the computer, that there is a washing machine maybe washing clothes in the kitchen, or that food is, well preserved in the fridge despite of high temperatures, right? So all this has been automatized, and this is why our life nowadays is so much, more comfortable, comparable to what it was 100 years back. Whatever country you are living, our life conditions nowadays are much better than they were 100 years ago. And this is precisely because this big goal that was advertised by Aristotle has been driving our civilizations continuously, right? So make processes automatic so that humans are more free, and you can devote yourself to do mathematics, music, or to bike or to hike, right? But then you are not a slave anymore of the daily duties that, robots or machine can do for you. And there are several reports on the state of the art in control theory that has been in particular published by the American Society SIAM. I like very much the front page of this 2003 report, right, on controlling an information-rich world, where you see here a number of gadgets. So you see here the classical governor engine for the ball regulator engine for the governor. That was the key element of the success in the Industrial Revolution. You see a chip, you see a robot, you see an old thermostat, You see the first airplane of the Wright brothers. You see a cancer cell here, some telecommunication systems, aeronautics, and so on, right? The concept of cybernetics was introduced by Ampere. It was forgotten for a while, and then it was somehow revived by Norbert Wiener in his book Cybernetics, who defined control as being the science of control and communication in animals and machines. So you see that this is an advanced definition of what the aim of Aristotle was originally, right? And it's in this very definition where you realize how close the goals and the contents of this field are to those of what we call nowadays artificial intelligence. Is not this really the definition also of what artificial intelligence is doing? Is not the science of control and communication in animals and machines? Is not machines doing the work that we animals, humans, want them to do, right? Like even, write a letter of, application for, I don't know, visa for travel, for instance, for the embassy of the nation X that you are willing to visit, right? I think it's really the same, right? So in some sense, you see that science has evolved, mathematics has evolved, and in this evolution, the old topics get renewed. And to a large extent, I will say machine learning and artificial intelligence is the nowadays version of classical control and cybernetics, right? That in the past, they were dealing, was dealing with classical industrial processes like automotion on aeronautics. And nowadays, is more rather trying to understand complexity within data. We are applying the same kind of science, right? With, of course, new ingredients and very innovative ideas, right? As it should be. But it is basically the same discipline that is evolving, because now the applications are not, the classical ones, but are new ones generated by the new society of data and technology in which we are living. Yet, the classical discipline of control is evolving. You have robotics, for instance, and nowadays not only you have robotic cars, but for instance, in the American campuses, very often you can order, a coffee from your office, and there is a robot that will come from, the university, restaurant area to your office and send you an alert, an email whenever, the robot is, on the entrance of your building, so that you can grab your coffee without moving to the university restaurant area. Okay? Now, we are mathematicians, so we understand things much better once we get into mathematical formulations and models. Let me show you a result in control theory that, to a large extent, describes what is the very spirit of the discipline, and also is very useful to establish the bridge with the modern applications, in particular in machine learning. This theorem is due to Kalman, 58, 10 years after Norbert Wiener wrote his book, in which he was tuning the concept, or refreshing the concept of cybernetics by Ampere. So Kalman said the following. So this modeling is extremely important, because this, once you understand what the model is and you formulate the problem precisely, you have 90% of the answer already, right? So Kalman said the following. Assume I'm dealing with a complex dynamical system, but let me, to simplify things, make it to be finite dimensional. So we are in n dimension. It can be a particle evolving in 3D, or it can be a social network in which millions of people are interacting, right? And then the state of opinion, right? The opinion of every individual is one of the components of the state. So this vector can be just a point in R3 in classical applications, but it can be also a vector of millions of components. Okay, very good. And so the free dynamics of the system is x prime equal ax. So there is a connectivity matrix. For instance, if you build a WhatsApp group with friends, right? So A is the matrix indicating how the connectivity goes. Of course, there are some people that are more talkative than the others, and there are people that are closer and communicate more often, right, than with others. So you can gather this in this connectivity matrix, okay? So this can, of course, be also the space discretization of a PDE, like the heat equation or the wave equation, if you wish, using finite difference or finite element methods. In any case, you have this dynamical system, okay, driven by the matrix A, and then of components N. Typically in machine learning, in modern applications, N is large. If you are dealing with images, you know, N is the number of pixels of an image. So yes, an image is a vector in the Euclidean space, but the Euclidean space under consideration is of a huge dimension. So N can be very large. And then you have controls. So controls are, you know, the actions you can enter into this system through the actuators, right? That are aimed to, you know, to drive the state of the system into the desired configuration. When you are driving a car, it's just to get to destination, right? But maybe when you are dealing with, for instance, the photo folder in your computer, you open the photo folder in your computer, you see, oh, I have 10,000 photos. So you see you have 10,000 photos, which are 10,000 points in an Euclidean space of dimension of a huge dimension. And you want to collocate, to place all these photos ordered by some criteria, year, location, people, or so on. So this is like a huge dynamical system in which every photo has to move from the original location to the corresponding destination. And you want to do that, you know, by just clicking, right? So you have to grab one and put it there and so on, right? Of course, this is a task that nobody wants to do. You can try. And after 20 photos, you are already tired. So this is why it's much better to ask the computer to do that automatically. We will come back to this topic later. But this is a control problem. So actions entering into the system. But often, of course, you have to control a large dimensional system by just a few controls, right? So in particular, right, in a social network, there are often influencers, right? Influencers are those people that just, you know, write a few words, and this immediately spreads all over the network and changes the state of mind on this network, right? These are the influencers. For most other people, you know, we write messages and nobody cares. But the influencers, they write something and suddenly there is a lot of attention paid. There are many reactions, and then the opinion starts changing rapidly. So how can, for instance, one single influencer, one magic finger of a god or a dictator, right, can, you know, generate a new state into the system regardless of what the dimension is? This is the problem that Kalman formulated. And he said, well, it depends very much on the control operator B you have. You might have just M components on the control. M can be even one. One single control for many, many components of the system can do the job. The only thing you need to check, as he indicated, is to check whether the rank of B, AB, up to AN minus 1B is equal to N. If you have chosen the matrix B in such a way that this rank is full, then the system is controllable. It means that you will always be able to find a strategy for your control UT that will be able to drive the system from the initial configuration to the final destination you choose, right? And if for some reason, when you compute the rank, you don't get N, you get less than N, for instance, N minus 1, then the answer will be, well, the system unfortunately is not controllable. There is one component on the system that you will not be able to control. For instance, if you ask me, is the car controllable on the plane? I tell you, yes, of course, I can drive on the plane. And you ask me, is the car controllable in space? I will tell you, no, unfortunately it's not. I need an helicopter in order to go up in the vertical direction, right? And this is what, you know, optimal driving is, right? So when you apply these ideas to controlling cars, not only you can check that the car is controllable on the plane, but you can even compute the optimal control trajectory. And this is how the optimal parking goes according to the Pontryagin optimality system. that you can write down for optimal controls, right? You see that in just one maneuver, you are able to park the car. Of course, most of us are not able to do that so optimally, and we need a lot of zigzag in order to park the car. This is, because in practical applications, there is an optimal control, there is an optimal strategy, but it's not so easy to understand, it's not so easy to achieve, and therefore we operate very often suboptimally. Of course, we don't need to be optimal, right? So, very often suboptimal is enough, right? So we can use bike for transportation, but we don't need to be, the winners of the Tour de France, right? For doing that successfully. We just need enough time to be transported from, origin to destination at the given time window, okay? But in the end, regardless of what we do, how deep our theorems are about the optimal trajectories and so on, in practice, we have to compute them. And this is why the classical tools of optimization, and in particular discrete optimization, are so relevant, right? In the end, the computer needs to assist us. We need to use them. The computer understands only discrete problems, so we have to discretize everything and then try to go for the minimum. And again, this sounds like a very elementary problem, right? We learned that in the first year calculus class. Every continuous function in a compact set of the Euclidean space, in a bounded and closed set of the Euclidean space, has a maximum or a minimum. So this is already in that theorem. So why then things should be so complicated? Well, because, even if we know a priori that there is a minimum and a maximum, or maybe multiple ones, finding any of them efficiently on the computer can be extremely hard. And this is why these are topics that are still demanding plenty of research. There are, of course, also nowadays very efficient tools that you can employ, like IPOP, that was developed, I think, in Carnegie Mellon originally to deal with problems of, regulation of complex reactions on chemical networks, right? And that you can use freely online, right? Or download the software in your computer, and that will solve all kind of finite-dimensional optimization problems. You can try yourself, right? Try the problem you are dealing with, and then check whether you are able to defeat IPO. Probably you will not. You can write, of course, your optimization code yourself, and this is something that educationally is very interesting to be done. But in practice, probably IPO will do it better and faster than you are doing. So maths are still in this process that was already, advertised and announced, flagged by Aristoteles and the Pythagoreans. But of course, we deal with the modern challenges, and these modern challenges go very much into the fields of big data, neurosciences. Understanding human brain is already a magnificent challenge in itself, and this is very much consistent with what our Nobel Prize winner for nanosciences indicated, right? So we don't need to think on science fiction. We can, but we don't need it. Just understanding the surrounding nature is sufficiently complex. And this, of course, applies to our own human brain and also human interaction in a society that is getting more and more complex. We see nowadays all these challenges that the humans are facing with the ongoing wars. It indicates that already human relations are also dynamical systems, complex enough so to require of the best mathematics for control. So now in these lectures, I will tell you a little bit about the mathematical foundations of control theory, some of the mathematical foundations of control theory. In the end, we will get into more modern applications related to machine learning. Let me just motivate it by a few slides before we go to a break. So this is probably one of the simplest applications in machine learning you can think of. This is what is called supervised learning. Okay, so what does learning means? So this is the first thing. What does learning means? Well, allow me to give a very elementary definition of learning. Learning will be building a function. Okay, so why do I want to build a function? Well, actually, I want to build a function because I want to build a robot. I want to build a robot that will classify trash so that plastic items go to the yellow basket, glass ones to the green, paper ones to the blue, and organic ones to the gray. And you ask me, why do you want a robot? Why you do it yourself? Well, I can do it myself, but this is not the best exercise. This is not the one I like the most, right? I prefer to devote myself to other things. So I really would like to have a robot that will classify trash, okay? And this is something that, of course, every city has to have in order to make humans free of this, painful task, okay? So a robot is a machine. A machine has to be endowed with a computer program, and a computer program is just the informatics version of a mathematical function. So we need a function that will be able to place every plastic object into the yellow basket and every glass object into the green basket and so on, okay? So what we do in supervised learning, we say the following, okay, let me train this function. So train means, let me build this function so that it's interpolating a sufficiently large number of items, according to the corresponding basket. So let me take a collection of items. So in this case, 32, because I have taken 8 plastic, 8 glass, 8 paper, and 8 organic. So I have taken a collection of 32 items, and I am building a function, right? So that, it takes each of these items and place it, allocates to them the image, right, in the corresponding basket. And the 4 baskets can be, for instance, placed in the space R2, right? So each of them in one of the, the polar points, okay? Very good. North, south, west, and east. Okay, very good. So, but still, I need to make this to each of these objects to become a mathematical object. Well, it's very easy. Just take a photo. With this photo, you have the pixelation of every object, right? And this place, according to the number of pixels, every object in a space of dimension D. So you see that now you are in dimension D, the objects are living in the Euclidean space dimension D. We are also, the images are living in dimension, for instance, 2, where the labels are simply yellow, green, blue, and gray. And my objective is to build a function that is taking each of these objects and placing them in the corresponding image, right? So this is what is supervised learning. And what is the goal? The goal is that if you do that exercise properly, if you are able to build this function so that all these 32 items have been placed properly, probably this function will then be able to, given a new object, right, realize where it should go, right? And that's, the aim of automatic control. So back in '89, there was this paper by Sibenko where he introduced the so-called universal approximation theorem. Well, maybe he was not introducing it. There was already a number of results in this direction, but this was, Sibenko made this very systematic and very nice, very easy for us to understand. It's a very beautiful application of Hanbana, right? He said, the class of neural networks, the class of functions you can achieve using neural networks is dense. Density in the context of machine learning is renamed as the theorem of universal approximation. Okay, I will come back to this later. And people said, well, fantastic. If neural networks are dense, this means that with neural networks, I can achieve all the functions I like. In particular, I could build the function that I was aiming here for this supervised learning exercise. And indeed, this is true. You have to build the coefficients of this neural network properly. And as you will see, our perspective to this topic is that the mathematical tools you need to learn, right, to be able to train these neural networks to choose the coefficients. Training is just choosing, optimizing the coefficients of this neural network properly, is the same tools you need in order to do classical control applications. And in this way, it was our former PhD student, now he's a researcher in INRIA in Paris, Borjan Geskowski. He developed this beautiful video in which you see indeed how a deep neural network is able to classify rather successfully, right, items, right? You see how out of an initial configuration in which yellow, green, and purple were mixed up, they evolve, right, along this deep neural network that we visualize as a dynamical system. And you see how the purples go with the purples, the yellows go with the yellows, and the green go with the green. You will say, oh, but this is not perfect. Indeed, this is not perfect. This purple is with the green, so this is a default. So the deep neural network we have built was able to classify items, but only is doing it successfully 99%. But this is, something you have to live with, right? You need to develop algorithms that are more and more efficient. But I remind you, as Einstein said, you will never get to perfection, right? So you need to keep evolving. And this is something, it happens also when we use our artificial intelligence tools. If we ask, our computer to automatically classify items, I don't know whether you ever tried, but you will see that, for instance, very often, in your folder, you will find the photos of your brother or your sister. Why? Because, the computer identifies the analogies with different people and then is confused, right? So at a given time, you are, for instance, the green could be all the photos of myself. And then I discover how by error, the computer has placed in my folder the photo of my brother. But this is not so bad, because actually when I'm walking in the street, people tell you, oh, your brother and you look, more and more alike. So the same analogy that we humans identify is what is, confusing the machine. Machines are, aimed to do the work of humans, but please don't expect that the machines will not face, in a way or another, the same difficulties as we humans do have, right? Now, you can wonder, well, if machine learning, we will present some more advanced topics later, right? But I mean, if machine learning were simply the application of classical or more or less tools of mathematics that we already know, why is so relevant? Why is getting so popular? Why people are getting even rich by doing this, right? So in order to get an idea of how relevant this revolution has been, think, for instance, on Google, right? 26-year back. So these two, I don't know, master or PhD students in computer science or mathematics, I don't remember, I think in Maryland University, right? They said, listen, internet is getting bigger and bigger and bigger, and is really a mess. When you want to look for something, right? So now we have Google Scholar, and it helps a lot, right? So if I want to know what are the main references on a given topic, right? So I can do it immediately, right? So I can say finite difference wave equation, and you immediately will get a list of papers. Not all of them, maybe the ordering is not perfect, but this is very helpful. You can start clicking there, and very probably, in a few minutes, you will have a good perspective of what is the state of the art, what are the most, relevant articles in the area, and so on, okay? So they said, internet is growing in our society 25 years back. We need tools to navigate in internet. We need to, to have intelligence tools so that if someone is looking for the biography of Einstein, right? When this person writes Einstein, it gets to the Wikipedia page of Albert Einstein, and not to the location of the Einstein Street in Madrid, because there is an Einstein Street in Madrid, right? So very likely, the person that is looking for Einstein is probably not looking for the street in Madrid under the name of Einstein, but is probably more interested on the life and work that Albert Einstein did, right? So what they said, let's use, the classical Perron-Frobenius theorem that says that for a given symmetric definite positive matrix, the first eigenvector has only positive entries, and let us use the relative values of these entries as the main criteria for ordering, the importance of the different web pages that are referring to Einstein. And what is this symmetric definite matrix? Is somehow the connectivity matrix in the internet. So then you could wonder, how could it be? Well, this is how it happened, right? Two master or PhD students that were thinking on how to put some ordering into the internet. They had this bright idea of using one of the fundamental theorems on algebra, right? Like Perron-Frobenius theorem, and implement it successfully in a computer program. And they immediately saw that this was a very powerful tool that led to the new revolution of Google, that nowadays is something that belongs essentially to the life of most humans, right? So you see how we humans, despite of having many other defaults, were able to develop mathematics, starting with the Pythagoreans or even earlier, right? But let's say that everything started with the Pythagoreans in our civilization. We were able to develop the Industrial Revolution. We have developed the revolution of robotics, of control, automatic control, right? Machine learning, artificial intelligence. We don't know how things are going to be 50 years from now, but what we know is that, this new universe will be written again in the language of mathematics. More mathematics will be needed. New mathematics, we don't know which mathematics will be developed in order to tackle, these challenges 50 years from now that for us are very hard to imagine. But certainly mathematics will play a fundamental role also, 50 years from now. And this is why mathematical education and the kind of exercise we are doing today is so important, right? And luckily, not only listeners learn, but also the teacher, in this case, me, learns a lot when talking to you. And I will be happy to listen to your questions, and then we can have a discussion. When arranging the slides for these lectures, Abdou and Francois recommended me that by the end of each lecture, I post one slide. This slide refers to an article we published 1.5 years ago in Siam News. It's a dissemination article. And there I explain, in plain language, it's very easy to read, what is our perspective to this, always enriching interaction between classical control theory and machine learning. With this, we can maybe make a pause, and maybe we can start. What do you think, Francois and Abdou? We can start at, it's 11:18 now. We start at 11:35 in 17 minutes.
Yes, that's very, very good. So first thing is, thank you very much for your very nice talk. So we can restart in, as you say. So you said 11:35. This is what you said?
Yeah, in 17 minutes. So in this way, also, if people have any questions, maybe we can address these questions beforehand, and then I go to the second section.
Very good, very good. Are there any questions now? Just now, just to see if some of you have some questions online.
There are some comments. Oh, there is Abdou. Attendance certificates. Hello, everyone. Okay. Yeah, so people have time to think on some questions, and we can start at 11:35 with a couple of questions. Just drink a cup of coffee, because remember that coffee is the fluid number 4. Right?
Yes.
So I think the ordering is first blood. Without blood, there is no body. The second one is air. We cannot stay very long without breathing, right? And then the third one is water. We can stand a few days, but not very long either without drinking. But then fourth is what the fuel we need to, to continue with the second session.
Completely agree.
Okay, see you then in now 16 minutes.
60 minutes. Okay, thank you again.
Tout à l'heure. Okay. Good.
So welcome back.
Yeah.
Do we have any questions on the chat? Don't see any questions. So please, before we restart, feel free to ask any questions if you have.
There is one question that was forwarded to Enrique.
Yeah. Yeah, that's a very interesting question. Actually, it's very philosophical also, right? So the question says, question one, why is that some simple human activities such as hunting or playing football are very difficult to model using differential equations, while some phenomena such as launching a satellite into space, celestial mechanics, have been successfully modeled using differential equations? Could it be that the human mind is making something humanly simple more complicated than necessary? Could it be that we have not invented the appropriate mathematics for some things which are humanly simple? That's a very interesting question, actually, right? So you see, if you, for instance, you see my note, right? So you can see the iPad, right? The blue, can you see the blue background? Yeah. So we take 2 points on the plane, right? We know the shortest path is the straight line, right? Now let us do it through the calculus of variations. Then what do you get? You say, well, I have to consider all possible arcs, right? I have to consider all possible arcs, right? The arcs are parameterized curves, right? That are taking the value A at the origin and the value B at the end. And I have to minimize, then the arc length, right? For all these, this is the class C, of course. For all parameterized curves in this class, I have to minimize the arc length. And the arc length is this, right? So now you say, well, now this is a problem on the calculus of variation, but you see that this is not one of the easiest, right? So in which class you have to minimize? So what is the topology I should put here? So it's certainly not Sobolev H1 because this is just involving the norm, the L1 norm. So you can think on the Sobolev space W11, but then a minimizing sequence is not guaranteed, to converge in W11. So then maybe you say, oh, then I have to do it in BV. Okay, then fine. In this way, you prove the existence of the minimizer. But we want to know what the minimizer is. Actually, we know that the minimizer is the straight line, right? There is no secret on this. So how can I get this minimizer? Well, I have to find the Euler-Lagrange equation associated to the minimization of this problem. For this, I need to compute the Gateau derivative for this integral. And well, the Gateau derivative for this integral, given that I am, computing it on a BV function, is not something that is so straightforward, right? Actually, it gets complicated. So, this is an answer to your problem, right? So there are things that are obvious and that indeed, when we try to make them mathematically rigorous, they can get very convoluted, right? So this is why one of the first principles in the philosophy of science is the one of the Occam razor that says, listen, you have to adopt the model that better fits your problem, meaning that is among all models, the simplest one that is able to give you a sufficiently satisfactory answer, right? So then if you will ask me again, what is the shortest distance between 2 points, A and B? I will tell you, well, the answer is the straight line, right? And maybe the proof I will try to do will not the one I started doing using the calculus of variation, but rather simply a more geometric proof indicating, well, as soon as, you are introducing some curvature on your path, I can fit here a triangle, and then according to the Pythagorean rule, right, this will never be the shortest path. So a geometric proof using Pythagoras' theorem will be sufficient, while getting into the calculus of variation can be more complicated. So the first thing we have to say is that, the role of mathematicians is not only to solve problems, but also to formulate problems in the most intelligent manner, so that you get the answer you need to somehow a minimal cost, right? But then, on the other hand, it is true, as you anticipate in your question, that we as humans, we do many, many, many things that are not easy to formulate mathematically, right? So actually, there are many. So we observe colleagues, for instance. We observe colleagues, and we say, "Oh, this colleague, this lady, or this man, I like very much the way she or he works." And then I ask you, "Can you please describe why do you like it?" Well, I have some intuition, but I cannot be very precise. But what I can observe is that she or he is doing that very successfully, because explanations are very clear. The problems that she or he handles are always very interesting. The kind of results she or he achieves are always very innovative, and the proofs are very transparent. Okay, you have some idea, but if I ask you, can you be more precise? No, I'm sorry, I cannot. There are things I perceive and I understand that I'm not able to explain. Actually, how do we function as humans? So machines are very much behind humans in many aspects. In many others, they are advanced, more advanced. So for instance, ChatGPT is faster than us, for sure. If I ask you, please write one page, I was mentioning to you before, right? So the comparison between traumatology and physiotherapy. So you could add traumatology, physiotherapy, podology, and I don't know what else kind of, medical specialty. If I ask you, can you write one page describing briefly the main activities that each of these specialists develops and making a comparison? Well, you will need at least half an hour to do that, right? Or even more. And even with the assistance of the computer, you still need half an hour to write a page, comprehensible on this topic. And ChatGPT will do it in half a minute or even less. So machines are more advanced than us on some tasks. On some others, they are not, right? We observe, the environment, and we can make decisions in real time on issues that will be very hard to model, right, on the computer. So nowadays we see how, for instance, the discussions about, how artificial intelligence can help the detection of cancer, for instance, of course, right? So, the machine can help the doctors to see better, right, in some specific circumstances and some patterns, right? But you will not to be, you would like to be diagnosed fully by the machine without, the support and the control of a doctor with a lot of experience when it gets to important things, right? Important decisions you have to make of whether you want to go into eye surgery or not. You don't want to just this to be decided because you were clicking on the internet, right? You want to go to a very expert of ophthalmologist that will tell you, yes, you should do that, or maybe not, right? So humans are still ahead in many other tasks, but machines are learning fast. And then machines are learning, trying to mimic what we do. For instance, this is what reinforcement learning did. What is reinforcement learning? one of the big topics in machine learning. Reinforcement learning is about combining basically model identification and control. So when we go to class and we teach a master in applied mathematics, we say to students, well, first you have to study the book in mechanics, continuum mechanics, right? Because in continuum mechanics, you will find the models for elasticity, for fluids, and blah, blah, blah. Then you have to do analysis and go through, functional analysis and probabilities and Sobolev spaces and so on. So once you have done that, you have to take the course on applied functional analysis for solving PDEs, and then you know how to solve PDEs. And once you have done that, you have to take the course on numerical analysis, and then you know how to discretize the PDEs and solve them computationally. And then in the end, you take this optional course on inverse problems and parameter identification, where they will tell you how out of measured data you can identify your model properly. And then once you have done all this, you start, taking the course in control. Then the teacher in control will tell you how to manipulate the system, how you can act on the system, like Kalman explained, to, drive the system to a given destination. But this is not how we operate in real life. If you offer me a new telephone, the telephone comes with 500 pages of instructions. I don't go through the instructions. What I do is I just turn the telephone on and then start interacting. So by interacting, I learn. So from the very beginning, I interact with the system, with the machine, so I am controlling the machine. And every action I do, I observe what the output of the machine is. And by this observation, I learn about how the machine behaves. The same when you change the car. You sell the old car, you take the new one reacts very differently. You say, oh, this one is much smoother. The acceleration is much, efficient. Or the brakes are also much more efficient. So I have to brake more carefully. In the old car, I have to press like hell so to get the car, stopping. Now it goes very smoothly. Or the change of gears is now automatic. I don't need to do anything. I just to keep my hand quiet because, I don't need to interfere. So you learn by doing. So reinforcement learning is about, controlling a system with very partial information and then gain information on the system. So solve the inverse problem or the parameter or the model identification problem simultaneously as we are operating. So this is the theory of reinforcement learning. And this is nowadays working very well as well. And this is being applied in many contexts. But, there is always this tension between humans and machines. We humans decide for which task we want to develop machines. And then we put all our intelligence oriented in that way. And we succeed on building the machine that will defeat the human in this task. For instance, Kasparov lost, against the machine in chess many years ago. The winning of the machine facing the Go world champion was much more recent, right? But of course, we still don't have the robot that will play soccer like Messi, right? That's true. Will this come? Well, it looks unlikely, right? But maybe one day, because so far, right, in every task that we decided to invest, the machine ended up doing it better than the humans, right? But then, while the machine is trying to learn how to play soccer as Messi, probably we will invent other sports, right, in which we humans will be still more advanced.
Thank you.
Dear professor, is there a rigorous way to do stability analysis mathematically of a reinforcement learning based controller? That's also a very good question. So reinforcement learning is a very broad topic. You can see very nice lectures by Vertsekas, professor in MIT. So this was mainly developed, I will say, by computer scientists and engineers more than mathematicians. So I think there is plenty of room for mathematicians to get interested on this topic. And actually we should, right? So this is a very good topic for young people to investigate from an applied math perspective, right? So how things occur. So you see, Richard Bellman, you know all this concept of the course of dimensionality. Actually, the course of dimensionality was coined by Richard Bellman. Bellman that was, following the tradition of Wiener and Kalman, in control theory in cybernetics. He realized, right, what we were saying here, right? He was looking to these kind of problems, find the optimal path from one point to another. And then he coined the term of the principle of dynamic programming. He said, well, it's very simple, right? So in principle, it shouldn't be that difficult because the optimal path from A to B, you can just start from B and make sure that in any intermediate step, you are always, taking the shortest path. So then in the end, you can say, oh, if I have to go from A to B, I will do a finite number of steps. And the only thing I need is that in every step, right, I guarantee that I'm taking the shortest path. Fine. That's very simple, especially when you think time discrete instead of time continuous, right? Very good. But now assume you are in a high dimensional space. So here the drawing is in 2D. But as we have said before, when you are classifying photos in your computer, every photo has thousands of pixels. So you are in an Euclidean space of thousands of dimensions. So even, when you are just thinking on the last step, whenever you are in a given position in the Euclidean space, and you want to decide in which direction you are walking, assume you have just done a finite difference grid, right? In 2D, when you do a finite difference grid and you are sitting here, well, the number of possible choices are, 4, or you want 5. You can stand where you are, 0 motion, or you can move to any of these other neighboring destinations. You have 5 options, right? But this is on the plane. What happens when you are in thousands of dimensions? Well, the number of, possibilities explodes. And then even this simplest problem of making, implementing what Bellman indicated, listen, if you want to go from A to B in the shortest path, it's very simple. Every time you make a step, guarantee you are doing the best possible option, right? And the best way to do that is to do it backwards, right? Fine. If this was the problem, why it gets so difficult? Well, because he observed that in every step, when you are in high dimensions, the number of possibilities is so huge that you face the course of dimensionality. There is no human mind that can explore all possible paths. And then eventually, the machine was able to defeat the Go world champion. The machine was trained, on many, many, many plays that have been recorded. It was then trained, by playing many, 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 many new times. So in this way, what the machine did was to build within the machine, a landscape of paths within the game of Go, richer than the one that even, the brain of the world champion could gather, right? And because the machine had a, better map, of course, could find a better way and then defeated the world champion. So it's like when you are just traveling along a city, right? If you give me a very rough map, I will not be able to visit many places because the places will not even be indicated. If you give me a map with many details, I could even be able to visit the narrowest street, which are probably the prettiest ones because nobody goes there, right? And this is where, you know, the nicest statue or fontaine has been, you know, fontaine has been sitting there for centuries for you to visit. So it's a matter of having enough information to make the choice. But of course, if you have a lot of information, then you have the embarrass of choice. This is why, like when you go to a restaurant and you see that the menu has 20 pages. Well, I would prefer a restaurant with just one page so that I can just choose, right? Salad, soup, fish, or meat, right? So reinforcement learning is being very successful, but, you know, explaining the mathematics of reinforcement learning is a great challenge. So there is a lot about gathering more information. We all understand that with a better map, you can make better choices, but then you face the cost of dimensionality. Choosing in a very rich universe is more difficult because there are many possibilities. So what do? Well, you use the two hands you have. And in the two hands, we have, on one hand, we have gradient descent, classical optimization. You do derivatives and you go down to better choose. And on the other hand, you have Monte Carlo, random choice. And this is what reinforcement learning does. But of course, there are many algorithms and the proofs of the convergence of these algorithms. Maybe this is a topic that François de la Rue could tell you more, right? This is certainly a very innovative and challenging topic. I don't know whether there are other questions. Okay, very good. So let's then move then to the second lecture. Okay, so now let's be more mathematical. So this is the model of Kalman, the very definition of a winner. And here you see this diagram: input, controller, control process, output, open loop system. So this is a very important distinction in control theory, right? Open loop versus closed loop, right? And is related also to reinforcement learning and other topics in control like model predictive control, right? So open loop control à boucle ouverte or boucle fermée. Closed loop is feedback in English, right? So what does closed loop mean? Closed loop means that in every time instant, I am able to decide about what the control I should implement, right? Just by looking to the state xt, right? So closed loop will be a control ut that you can just determine by knowing xt. In practice, things are not that easy, right? And this is why experience matters, right? Because in many, even in life, right? In human relations at work or in family with friends, experience helps, right? And experience teaches you that in many, many processes, you cannot make optimal decisions just by looking to the state of the system at time t. You have to keep, in mind the history, right? So this is why, it's easier, when you have good friends, the friends know you well, they can help you more, right? Because they know about your past history, and then they can react in a more intelligent manner when they are talking to you or they are advising to you, right? Because they don't see just your state, your mood at this time, capital T, but they can, figure out, what is the past history and how this is affecting and how then, according to all this, you should behave in the future. So feedback, of course, is a dream, but it's a dream that is not always achievable, right? So in principle, right, the simplest problem we can deal with is the one in which, I give you the time window 0 capital T, and I tell you, please take your time. I give you the system x prime equal ax. I know we start at the initial position x0. I give you the time window 0 capital T. I know that my controller is given by the operator B. This operator B, recall that on X, there are n components, very many possibly. And on U, there are just m components, maybe very few, maybe just one. So the control operator is just the machine we have to control the system, right? It's just the machine we have. We cannot change the machine. B is given. Someone has designed the machine for us. We are given this system. The only thing we can do is we can choose our control strategy. If U is an scalar, the only thing you can do is just choose the intensity, U up, U down, like when you regulate light, on and off, basically. That's the only thing you can do. Or with the heating device, you can turn it on or turn it off. That's the only thing you can do. And with this, you have to regulate temperature, right? If the heating device B has been chosen properly, it has been well calculated, well placed in the room, it has been the size, the power of the engine has been calculated for the surrounding temperatures and the volume of the room and the geometry of the room, then you will be able to heat, to regulate temperature successfully by making a good choice of U. But if the machine B is insufficient, I'm sorry, not sufficient power, you will not be able to heat your home when temperatures are too cold outside. Okay? So let's try to do it open loop. Someone could complain and say, no, I cannot wait that long for you to compute the control. I need it, I need that your decisions I made in real time. And this is why often also we make mistakes. Not because we don't know how to adopt the best strategy for tackling a specific problem. Is that because sometimes we are not given, the time to make a decision, or we don't devote sufficient time to meditate, to think about the decision. And then you buy something, and after you buy, you say, well, if I have thought on this a bit more, maybe I will not have bought this bicycle, but maybe I will have bought an electrical one, because now I realize that, in Nice, the slopes are so huge that maybe with electric, I would have done better. Okay, but now you bought already a non-electrical bike, so yeah, you have to live with it. Okay, so open loop. How can we first prove the Kalman result? And can, out of the proof, we learn how to also compute the optimal controls? So this is actually very elementary, but extremely interesting as well. So you see, write the variation of constant formula. So the goal is to find the control US so that the trajectory that is departing from x0 will get to a given destination in the given time capital T. So then this is the free semigroup, exponential of AT, the matrix A. I mean, A could be nonlinear, could be time dependent, then the writing will be more complicated, but the idea will remain, right? And then, of course, if I don't do any control, if I do nothing, U equals 0, this is the free dynamics, and this is what I get. And of course, this will arrive wherever the destination is, but certainly not necessarily to x1. So if you don't do anything, the system will go in the final time to exponential A capital T x0 and not necessarily to x1. So I have to correct the dynamics by introducing the action of the control wind, the control U. U will be like the wind, right? That will push the dynamics so that instead of landing on exponential A capital T x0, it lands at x1. Okay? Now, you say, oh, but this is fantastic because we are in dimension D or N. We are in dimension N, finite dimensions. So here, I need to find U so that this quantity here, when evaluated at capital T, is just equal to x1. So I just have N equations. And I can take it in an infinite dimensional space because I can make an appropriate choice of u at any time t. So I have an infinite dimensional space, u, for just solving a finite number n of equations. So this should be easy. Well, not necessarily. Our intuition here fails. So here I give you an example. You take, for instance, a system 2 by 2. A is the identity matrix, and B is the operator 1, 0. And then when you write this system in the form of scalar equations, you see that the control u is entering in the equation of x1, but the equation of x2 is totally independent of the control u. So this is an example of system that is not controllable. So two equations, one control, in this case, the system is not controllable. So is this just a matter of counting dimensions? Not really, because you take the harmonic oscillator now. This is a second order differential equation. This is controllable. Why? Because all scalar equations of high order are controllable. Why? Because, you give me initial position, you give me the final one, and I can always, I can always connect the initial position with the velocity you like, with the final configuration, with the velocity you give me. And out of this, I can read off just the control as being x double prime plus x. So all scalar equations like this or like this are controllable, right? And when I write it down as a system, I see that again is a 2 by 2 system with one control. So you see that the controllability of a system is not a matter of dimensions. There is something more. Okay? So now, in order to understand better how this goes, let's use duality. As you know, duality is one of the critical tools in convex analysis, in optimization. Actually, this is what Lagrange said about Lagrange multipliers, right? So he said, Lagrange said, if you want to minimize a function f of x over the level set gx equals c, you have to look to, right, this Lagrange equation. And you have to pay attention to the Lagrange multiplier lambda, right? That somehow this is the dual problem, right? And you say, no, I'm not interested. You say, listen, no, I just want x star. I don't want to get involved with the computation of the lambda. And then I tell you, I'm sorry, you have to, because unless this is the free space, the total space in which the critical points are gradient f equals 0, if you are looking to a constraint optimization problem, there is a constraint. The constraint influences the Lagrange, the optimality conditions, the Euler-Lagrange equations, and you have to understand, you have to compute the Lagrange multiplier to understand what the solution is. So the same principle here, right? We say, listen, we want to deal with the control problem, but the best way of dealing with the control problem is to look to the adjoint. What is the adjoint? Well, the adjoint is just the algebra differential adjoint, like in the theory of distributions, right? So you just swap A into the adjoint A star, time into minus time. The initial data for X becomes now the final data for the adjoint state phi. Of course, phi also lives in Rn, right? And then we just do integration by parts. I say, listen, go to the equation of u here, right? Go to the equation of u, multiply this by phi, scalarly in Rn for every time, do the integration by parts, and this is what you get. We get this equation here. Yeah. So here, just to simplify the problem, right? In the control problem, I'm just assuming that the destination is 0, just to simplify things. Otherwise, we just write an extra term for every x1. But I'm just writing things with x1 equals 0. You say, oh, and so what? I needed a control u so that the solution of the system reaches 0 at the final time. I have written this equation for u. I integrate with a phi. and then I do integration by parts, and I get to this equation for every phi. Well, this is just integration by parts, fine. And so what? What do I learn from that, right? Of course, you know, for instance, you see how in the term the integral of bu times phi, I have used the adjoint to put the b into the phi in a form of b star, like in here. But how can I use this identity? Well, to me, this doesn't seem to be very clear. Let's see how many phi's I have, how many solutions I have of the adjoint equation. You say, oh, you have many of them, infinitely many of them. Yes, but what is the dimension of the space of adjoint state? Well, the dimension is, you know, n. Why? Because here it's sufficient to take any of the basis vectors, right, of the canonical basis of Rn as final data for phi t, right? And there you encode the solvability of this problem for every phi. So you see that here I just have n equations. Okay, good. So I'm looking for u, again in L2, in an infinite dimensional space, and I have these equations to be fulfilled for every phi associated to any of the canonical vectors, right, of the space Rn. So n equations again with infinitely many, right, unknowns. On the other hand, you know, you see here the classical structure that we are used to. For instance, in last Milgram lemma, you remember in last Milgram, right? We have something like A, U, V, L, V for all V in V and U in V, right? So we are looking for U in a Hilbert space V so that there is a bilinear form, A, U, the unknown applied to the test function, like in here, the bilinear form. And then there is a linear form. And this is a linear form, right? Because, you know, this initial datum is fixed, and this is being applied on phi 0, right? Well, this looks like bilinear, but things are different in nature, right? Because here phi, right, is the adjoint, and I have here a B star, but here U is an arbitrary element. What happens if I do, for instance, the ansatz that the control U I'm looking for is also of the same form, B star phi, right, for some solution phi, some specific, very concrete solution phi of this problem? When I do that, I realize that actually I am dealing with the minimization of this functional. So if now, you know, of course, in the beginning, you need to exercise this a little bit before you get familiar to it. But once you have seen what I have told you, this becomes rather immediate and automatic. My claim is, listen, if you want to compute the control, the only thing you have to do is within the space of solutions, right? Within the space of solutions of the adjoint system, just minimize this functional, okay? I will come back to the minimization of this functional later. But why I am recommending you to minimize this functional? Well, because if you minimize this functional and you write the Euler-Lagrange equation associated to the minimization of this functional, by just computing the Gateau derivative of this functional and saying that at the minimum, the Gateau derivative of the functional is just 0. By just doing this, you observe that the minimum of the functional is giving you the optimal control you are looking for. More precisely, the control you are looking for is just B star applied to phi hot. So here hot has nothing to do with the Fourier transform. It's just a way of distinguishing the minimizer of this functional. And what is the reason? Well, the reason is that if you expand, you do the classical Gateau derivative of the functional J, you get to this formula, and this is precisely the U we were looking for. So you see that by this duality technique, we have succeeded on replacing the original control problem to a minimization problem in which I just need to minimize this functional, right? The only thing I need to do is to minimize this functional, I just need to minimize this functional subject to the condition that phi is the solution of this adjoint problem. So we are in the context of the calculus of variation or in classical optimization theory. The problem could not be simpler. You know, this is a linear ordinary differential equation driven by the matrix A star. So given any phi t in the Euclidean space, there is a unique solution that will be given by the exponential of A star. Of course, this solution is analytic in time. It depends analytically on the initial datum. So the map from phi t into phi could not be better. And this functional here is, you know, the classical functional we encounter in the context of the energy formulation of PDEs, like elliptic equations, a la Lax-Milgram, where we have a quadratic part here, and we have a linear part here. Okay, fine. Now I check the functional J. I say, well, J is defined in Rn. Well, Rn is a Hilbert space. Fantastic. This functional J is continuous, of course. This depends, phi continuously depends on phi t. Everything depends continuously on phi t. This is linear. This is quadratic. The functional is continuous. Oh, then quadratic plus linear is also convex. Convex, continuous function in a Hilbert space, it has a minimum, right? But there is an extra condition that is missing. So what is this extra condition missing? I let you just think half a minute. So what is the extra condition missing? Coercivity. Coercivity, indeed. I need to guarantee that the functional is like a paraboloid going upwards, so that when I build a minimizing sequence, the minimizing sequence is bounded so that I can extract a weakly converging subsequence and so on, right? And then use continuity and convexity to guarantee lower semi-continuity. I need coercivity. Otherwise, it could be like a Gaussian in which the minimizer is lost at infinity. We need coercivity. Okay, good. So, but can this be coercive? Listen, what do I have here? Here I have a lot of information, right? Because at every time I'm gathering B star phi. B star phi is like a sensor, right? So B was the actuator, but B star is the sensor. You recall the definition of Norbert Wiener? Cybernetics was the science of communication and control, communication sensors, control actuators. We need the two hands. We need information so to understand the behavior of the system before we decide which action we are undertaking. So B star is like the observer, is the sensor, because, you know, here what we are doing, we are taking phi t. Recall that phi has n dimensions, so n can be huge. So phi is a vector that is evolving in a complicated manner in a huge dimensional space. But for instance, in the case where there is only one control, m equal 1, B star phi is just a 1D projection. It's just like a one single combination of all the components of the system. Can it be that just observing to one projection of this huge dimensional system, I recover full information on the system because I really need here the norm of phi squared. I really need coercivity. Can this be? Well, this can be done provided the control operator B or the observation operator B star is well chosen. You are looking for a trigger effect, for a domino effect, so that the rotation of the natural rotation of the system phi according to the dynamics that the A star matrix introduces guarantees that even if you are observing just one projection, all the components of the system will pass by, right? So you are in your balcony, right? And you are observing the complex dynamics of a crowd, right? And you want to make sure that you can see everyone. Well, the way you can see everyone is if everyone is passing, in front of your window, right? And this is what we are searching here. Is this true or not? Well, this was a fundamental remark done by Jean-Louis Lyons, who wrote this seminal article in Science Review back in '88. And he observed that this principle is not only true for ODEs, but for PDEs. What he said, listen, in order to guarantee that the system is, this functional here is coercive, what you need to prove is this inequality. So in practice, well, I mean, it might be easier or more difficult, but this is what it is. So if you know how to prove these inequalities for the system under consideration, then you can guarantee that the system is controllable. And when this inequality is true, we say that the system is observable. Why observable? Because I only observe, I only see this projection B star phi of the solution phi living in a very high dimensional space, but out of this projection, I have to recover full information on the system. Is that possible or not? Well, in this particular case, because we are in finite dimensions, all norms are equivalent. So the only thing I need is to guarantee that the quantity on the left-hand side is a norm. And for this to happen, the only thing I need is this uniqueness or unique continuation principle saying that whenever B star phi is equal to 0, then phi is equal to 0. Is this true or not? So recall that phi is a solution of the system. Phi is a solution of the system minus phi prime equal A star phi. So is it true that the solutions of this system fulfill this unique continuation property? If this is true, we have observability. And by minimizing the functional J, we have also the controllability and we have the control. And recall that because I have reduced the problem to building the minimizers of this functional, I have also discovered plenty of computational algorithms to compute the control. Because now computing the control is just implementing B star phi hat for the minimizer of this. And then you can use all you know about gradient descent, stochastic gradient descent, all you know about, finding minimizers for nice convex and coercive and continuous functions is something you can implement here and develop also many other variants. Okay, good. Now, you see that we have shown that if you have the unique continuation, you have observability. If you have observability, you have controllability, and you have a constructive procedures to build controls by minimizing coercive functionals that in particular, it leads to plenty of computational methods. For instance, if you were doing this for PDEs, then you will use gamma convergence, the numerical approximation of the PDE, and so on in order to build efficient numerical algorithms to compute numerical approximations of controls of PDEs. And then the question is, but do I have this unique continuation property? Well, listen, you have the unique continuation property if and only if the Kalman rank condition is true. Well, how can it be? Well, so here is the proof. I go quickly Details are written in the notes. So why the Kalman condition appears? Why does the Kalman condition appear? Well, the reason is the following. So recall that phi is the solution of the adjoint system. So it can be written that way. Phi is just driven by the exponential of A star out of the initial value phi capital T at time capital T. So this is the expression of phi, okay? Now, you are telling me that B star phi vanishes for all time. So you are telling me that B star applied to this exponential here is 0 for all time. But this is an analytic function of time. So this being 0 for all t small is like saying that all the derivatives of this quantity at t equal capital T, which is the initial time for the backward adjoint equation, vanish. But this is like saying that all these quantities vanish, right? Now, you see that, you know, phi t is in the kernel of all these matrices for all powers of k. But what does Cayley-Hamilton say? It says that every matrix is a 0 of the corresponding characteristic polynomial. So all powers of A star after n are linear combination of the n minus 1 previous ones. So you see that in this equation here, you can simply stop, right? You can simply say, listen, I apply for k from 0 to n minus 1, and all the information is already gathered here, because the rest that I am adding for greater powers of k by Cayley-Hamilton is not adding any relevant information. So then phi t is in the kernel of this matrix. And what do I need? Well, I need the kernel of this matrix to be reduced to 0. But this, as you know, is equivalent to saying that the rank of the adjoint is full. And you discover in this way, you know, the Kalman rank condition. So you see that the Kalman rank condition can be discovered also through the adjoint. And the only ingredients I have used for doing this have been the expression of the ODE solution as an exponential, the power series expansion at the initial time, Cayley-Hamilton, and then standard linear algebra concepts. Okay? Now, once you realize this, you can say many things. Like, for instance, that the space of, you know, controllable systems is open and is dense. Why is open? Because the rank being full is an open condition. If for a given choice of A and B, the rank is full, you make small perturbations and the rank is full. Why? Because the rank is full when there is an n by n submatrix whose determinant is different from 0, and this is a stable property. For the same reason, you can also prove it's dense, because a determinant being 0 is a property that occurs only with 0 probability, right? So most systems are dense, and most systems are controllable, and the controllability condition is stable. Yet in practice, of course, it can be very tricky to, you know, to check whether a system is controllable or not. Why? Well, because you see, you have to check whether this Kalman rank condition is fulfilled. If you open MATLAB, you see that MATLAB has a tool to compute the rank. Yes, but it will work only for small matrices. You don't want to do this exercise when n is equal to 1 million components, right? Because then you will have a matrix A 1 million by 1 million, and you have to compute all these powers of A up to 1 million. And then when you build this enormous matrix, you have still to check whether the rank is 1 million. Nobody wants to do this exercise. Even computationally, this is very demanding. And actually, one of the breakthroughs of the company DeepMind last year was precisely to use reinforcement learning tools, so machine learning tools, to multiply huge matrices. So you see that somehow here we are also in a continuous loop, right? We develop control to control systems. And, you know, we were using control ideas to solve the problems in machine learning, because this is really a very powerful device. But then when we get to the end, and we as mathematicians are satisfied because we have found an if and only if condition, then the practitioner comes and tells you, yes, but how can I check whether this matrix is full? And then you say, oh, my goodness, you are right. This is an impossible problem, computational. This is what Bellman indicated. So what Bellman said, be careful, because you will face the course of dimensionality. Even in those cases where you think that you have solved the problem, you will face the course of dimensionality, and therefore you will need, you know, the most powerful machine and the most intelligent algorithms to figure out. Okay? Then, of course, when you are moving into PDEs, you are in the infinite dimensional system, and then you have to really do the same when n is infinity, and then that's, of course, much harder, in particular because there are many different infinities, right? Okay, very good. But in principle, we got it done. And of course, you know, in general, by developing these methods and doing the estimates that the coercivity guarantees and so on, you can even estimate what the size of the control is. And of course, the size of the control is always proportional, right, to the distance between the target x1 and the solution of the free system, right? Because as I said, you know, the control is just the win you have to add, so to guarantee that the free dynamics lands in the correct destination and not on the one that the free dynamics was leading you. Once you have understood this, you can do many things. For instance, Bam controls. You see, the controls we have achieved here, they are very, very nice. They are very nice. They are of the form written here, right? They are very nice. They are U equal B star phi hot. So phi is a solution of the adjoint system, so it's an analytic function. So the projection B star is also an analytic function. So the control will be something very, very smooth. The control will be very, very smooth. But do you want to apply smooth controls? Well, these are not the simplest ones to deal with, right? In practice, how do we regulate light in our room? In our room, we say lights on or off. So we do on and off, 1 and -1, plus and minus. This is the so-called Bam control. So is the Bam control the best one? Well, it depends the criterion you employ. It's certainly not the most smooth ones, because, you know, it's even jumping, right? So the Bam control is something like this, right? But it has the advantage of being simpler. Why? Because the only thing you need to decide is in which time instances you are switching from on to off and from off to on, right? So now my light is on because I want you to have, you know, a good visio. But in fact, maybe I don't need it because there is enough light. So maybe if I turn the light off, you hardly see the difference. There is enough light coming from the outside. So I do off. But if I feel that, you know, the quality is not good enough, I can then turn it on again, and maybe you have a slightly better, say, video quality. Very good. So Bam is not as smooth, but is much easier to implement. And this is actually what we do in practice very often. How do I get Bam controls instead of L2 very smooth controls? Well, is this sufficient to do as indicated here? And you see the only difference here is that I have taken the square that was inside, I have taken it out. Why? Because now you see, if the Kalman rank condition is fulfilled, this functional is, again, convex, continuous, and coercive in the Euclidean space. It is coercive because the unique continuation property I need to guarantee that this is coercive is the same. B star phi equals 0 implies that phi is equal to 0. But now the square is outside. What does it happen then? When I compute the Euler-Lagrange equations now, what I get is this integral multiplying the sign of B star phi hat. this integral here is a number m, and therefore this means that the controls I have computed are always plus or minus m. And then what is the switching instances? Well, the switching instances are those in which b star phi hat vanishes. This is why, listen, things apparently are very simple, but in practice they are tricky, because now if I tell you, can you please compute perfectly the optimal bang control? Then it's going to be tricky. Why? Because first, you will need to compute the optimal adjoint state exactly, and then out of the optimal adjoint state, you will have to tell me exactly in which time instances the zeros of this function are located. And of course, this is something that you will never be able to do with a higher precision than the one that your numerical grid allows. So, things, again, that are conceptually simple can be tricky in practice, okay? And then one further remark that you can check easily here is that the controls I have computed here, not only they are successful, but they are also the optimal ones. So among all the possible controls that you can build for controlling a system, the ones that the adjoint methodology developed by Lyons provides by minimizing these functionals is the one that leads to the control of minimal norm. In that sense, you are doing the right thing, right? And then you can wonder, well, why you say that is the one of minimal norm, but why before we got one that was very smooth, and now we got another one, and now, so before we had one that was very smooth, and now we have one that is bang. So how can it be that they are both optimal? Well, because the control which is smooth is optimal in L2, while the control that is bang is the optimal, right, in L infinity, right? So depending then, when you say controls now are functions of t, then when you say that you minimize the norm of the control, now the control lives in an infinite dimensional space. So in which norm you minimize the norm of the control matters a lot, right? And this is why we say, listen, smooth controls are typically those in which you minimize the L2 norm, while bang controls are those for which you minimize the L infinity norm. Okay? Very good. So you can go beyond with similar ideas, and then, for instance, consider switching control problems. I will let you this as an exercise for your own reading. So switching control is also a very natural context in which you have two controllers. It's like two people cooperating, right? So you are writing a paper, a joint paper. So there are two writers, B1 and B2, right? But, well, in order to avoid confusions, you say, okay, so you handle it first, and then I will take it over, right? So you don't work simultaneously, because maybe, while one is changing the equation, you are making changes on the top of it, and then things get very confusing. So it's maybe better to alternate, right? So can I understand, for instance, in a system like this, when I have two controllers, like, for the car, electric and gas, electric and gas, electric and gas, how can I figure out what is the optimal way of alternating between electric and gas? Of course, the hybrid car does it for you. You don't decide yourself. You just guide the car, and you let the computer program of your car to decide when it prefers to burn gas or electricity according to the demand and according to, the level of the battery and so on, okay? How can you do that yourself? Well, again, the same kind of, rank conditions will be needed. But if you want to make it automatic, right? Well, you could say, I will plan it in advance. You could do something like this, like I will make a splitting of the time interval, and I will be using electricity during this time intervals, and then on the others, I will be using gas. But this is not how things are. I mean, if you are planning a long trip, I mean, you are driving, I don't know, from Paris to Dakar, right? You are doing the Paris-Dakar by car in a hybrid car. You don't plan in advance when you are using electricity and when you are using gas. Actually, this is done automatically by the engine in order to optimize performance, right? So if you want it to be automatic, you can also understand from the perspective of the calculus of variation how to do it, right? Because why? If I was using both controls, I will be just adding to the functional, the impact of B1 phi and B2 phi. This is the big operator B star applied to phi. If I were using the two controls simultaneously, the B1, B2 will become the big control matrix B, and therefore I will have here the full Euclidean norm of both projections B1 phi and B2 phi. As I said, if I were in this unrealistic situation in which I plan in advance the switching, I will take B1 phi in some intervals and B2 phi in the others. But I don't want to do this. I want, this switching between one control and the other to be occurring automatically according to the circumstances of the motion. So now it's very easy to guess what you have to do. Listen, if you have to define a function, right? So that you either use B1 phi or B2 phi according to the need, what will be the most natural way of introducing this functional? Well, the most natural way of introducing this functional will be to put here in the integrand the max between B1 phi and B2 phi. In this way, whenever B1 phi in modulus is more efficient, bigger than B2 phi in modulus, then you will be using the engine B1. And whenever, the second one, B2 phi in modulus is bigger than the other, you will be using B2. There will be, of course, some switching times, and the switching times, it will be those in which the two action of the two controllers is totally equivalent, is equilibrated. But apart from these switching instances, like in bang-bang controls, here the switching will occur from one control B1 into the other control B2. So you see that once you understand this duality principle between control and observability, observation, and this idea of, calculus of variation, idea of Lyon's, of tuning the functional to control, to build the suitable controls, you can do many things. And in particular, you can also build these alternating or switching controls, something that is very important in applications. Okay? Very good. So now let me get, in the last 15 minutes, let me get into a fundamental topic. And actually, the first paper, when you look to the books in the history of control theory, people tell you, oh, yeah, this started with Aristoteles when he claimed that humans should develop machines to make processes automatic. Okay, fine. But now more realistic from a math perspective, when does modern control theory start? People point to this paper by Maxwell. Maxwell was the one who developed ODs and Lyapunov-like ideas to understand the same of electromagnetism, is the same Lord Maxwell, to understand the dynamics of the governor. That was, the ball regulating engine for the steam engine in the locomotion in the Industrial Revolution, right? So you see, this was like 150 years back. So it's a relatively recent discipline in some sense, okay? So this is very much related to the problem of stabilization or feedback control. So now in feedback control, you say, listen, so far you were doing open loop control. But you see, your open loop control process was slow. Why was it slow? Because you see, yeah, I mean, you were very smart and you have realized that you needed to minimize this functional, this is very beautiful because you have linked control through duality with the classical calculus of variation and energy minimization for solving PDEs in the modern theory of weak solutions and so on. That's very beautiful. But this is very slow because now you will tell me that you need to apply a gradient descent algorithm to minimize this functional. And for this, you need to do plenty of backward and forward resolutions. It will take plenty of time. So this methodology of doing open loop is very nice to understand intellectually what the problem is about, but is not very efficient in terms of computing time. Because every time I change you the problem, if I now say, oh, sorry, there was a small error on the target, I changed the target a little bit, then you have to launch the whole process again and recompute the minimizer through a gradient descent algorithm with plenty of computational burden. So I really would like the control to be of feedback form. Why? Because if the control is of feedback form, the only thing I need to see is what the state is, and then the feedback will immediately tell me what control I should apply, right? So this is why, playing chess, things get even more complicated when you allocate to each player a short time for making decisions. You are pushing players not to think very long in every move, but to do it almost in a feedback manner. And when you have to do it in a feedback manner, then things become very tricky, right? And if you are, if you are really the most feedback player, then you are messy, and there is only one. Okay? So you see, this is why, high-level competition games are also beautiful to see, because you see humans reacting in a feedback manner in a way that is really sometimes unbelievable, right? Okay, very good. So it's not only about being very strong or very agile or very fast, it's also having a brain that is able to, compute the optimal play in a, faster than anyone else, right? Very good. So how can I analyze this problem? Listen, to do that mathematically, the simplest is to consider first the case where A is a skew adjoint matrix. So this is typically a Hamiltonian system. A is a skew adjoint, so AXX is equal to 0. So the energy of the system, if you take U equals 0, you will drop the control, then the energy of the system is conserved. And now the game to play is to determine a feedback control like in here, right? A feedback control like in here, so that when you plug this control into the system, so you make a priori the decision of building an L from Lyapunov in some sense, right? So you make a choice of an operator L so that the fact that you choose at every time t now the control U to be L of xt guarantees that you pass from a configuration in which the energy is conserved, so you are dealing with an infinitely, endless harmonic oscillator, you pass into an exponentially stable dynamics. So can this be done or not? Well, so now what we want is to find the L so that the new system generated by the matrix D, A plus D, BL, D for dissipative, so D equal A plus BL, is guaranteeing the exponential decay. And the question is, okay, but then you told me that A is a skew adjoint. What do I need from the B to guarantee that the system is exponentially stabilizable? Well, what you need is precisely, again, the Kalman rank condition. If you have the Kalman rank condition, actually, taking L to be B star suffices. Why is that? Well, the reason is the following. If you take L to be minus B star, then, the energy of the system now is time derivative of x squared, right? Half of time derivative of modulus x squared is equal to minus B star x squared. Oh, you see, this means that at every time step, at every time instant, you are dissipating energy from the system with a rate which is proportional to B star X. But this here is familiar to me. Why? Because we have seen that the Kalman run condition is equivalent to controllability, is equivalent to observability, and observability says that when you observe B star of the state, you see all the components of the system. So in some sense, it makes fully sense that Kalman plays a role here too, because here I am only dissipating B star X out of the solution X. And the question is whether I am dissipating a fraction of the full energy. And precisely what I need for this to be guaranteed is the Kalman run condition. How can I prove that? Well, the reason is very elementary. I just integrate in time, and I have that the energy at the final time minus the energy at the initial time is equal to the total energy that I have dissipated. And then, in order to guarantee the exponential decay of the system, the only thing I need to check is that during the time interval, I have dissipated a fraction, a volume fraction of the total energy. In other words, that there is some C so that this inequality is fulfilled. Because if there is such a C so that this inequality is fulfilled, I come back here, I use this inequality, I find this one, and when I put this together, what I see is that the semigroup from time 0 to capital T is a contraction with a contraction constant less than 1, which is precisely given by this gamma. And then once you have a contraction semigroup, by iterating, you just get the exponential decay. So you see that I have reduced in this way, by this energetic computation, I have reduced the problem of the exponential decay to the fact that I have the observability. But now the observability has to be proved for this system, or if you want, for this one. You see, but the problem is very similar to the previous one, especially because now in my observability inequality, B star is known. So B star being known, this other term here is known. And therefore, I am back to the system X prime equal AX. And then you will tell me, yes, Enrique, but observability before was for the adjoint system. Yes, but what was the adjoint system? The adjoint system was the one that was driven by the matrix A. And in this case, A being skew adjoint, you know, this is like writing here minus A star. So this is the adjoint system. So you see that magic, if we have a good understanding of the Kalman run condition through observability, right, then we also have the capacity of designing feedback stabilizers for the system. Okay, very good. So now let me tell you what basically what Maxwell did. So Maxwell did the mathematical analysis because, you know, when people discovered that the ball regulatory system was so efficient, they tried to design, you know, rotating ball mechanisms, even, you know, performing better. And what they have observed is that very often when they try to do, you know, the best possible design, the performance was poorer. So in some sense, more rudimentary mechanisms, not so elaborate, not so sophisticated, not so expensive, were doing the job better than others that were designed in principle to be magnificent. Why is that? Well, the reason for that is the fundamental principle of overdamping that can contaminate many of the problems you are trying to solve. So be careful. Human intuition is often wrong. And you can see that in the computation that Maxwell did. So Maxwell said, let me take this harmonic oscillator. M is mass and the rigidity constant are given, like in the finite element notation. And let me just add damping K. I check how does, you know, the system behave according to the damping. I can compute the roots. And what I observe in terms of the decay rate, so this is the constant K of damping, and this is the exponential decay. What I can observe is that in this specific system, so here I think the constants taken in this example were m equal 1 and r equal 1. When this happens, the best possible K you can choose is the one where, you never beyond the critical threshold 1. And the reason for that is that when you are computing the roots of this polynomial, quadratic polynomial, of course, the discriminant is relevant, and the sign of the discriminant is even more relevant. So our intuition that the more you damp the system, the higher the K is, the better the exponential decay of the system will be, the faster the system will decay. This is true only for K small. But beyond a given threshold, if you put too much pressure on the system can simply break down, can bifurcate. And this is what you observe when this, discriminant here becomes negative, and then your eigenvalues become complex. So our intuition of monotonicity of the response of the system with respect to the damping or control parameter K is true while the eigenvalues are real. But as soon as the eigenvalues get into the complex plane, and this is what happens as soon as K is greater than the square root of 4mr, then your intuition fades, and the root, which has negative sign here, is actually slower and does not necessarily behave better. By the contrary, the decay rate slows down. So this was the contribution of Maxwell about the decay of systems and the explanation of the stability of the governor. So now you see that here you could say, well, but here, what is the state of this system? This is a second order ODE. This is second derivative. So the state of the system is x and x prime. In your feedback, you are using only x prime. And of course, this is what happens. We have overdamping because we were only using half of the information of the state in order to design the feedback mechanism. The pole location theorem says that if in your feedback you use full information on the system, then you can design the feedback operator so that you can achieve the decay you want, right? But be careful, because in that case, this will mean that in my system, I am also modifying here, right, by adding a new, operator acting on X. If I just want a velocity feedback, then I am limited and confined by this overdamping phenomena. So this is a very challenging topic. Things got very, very far, as you can imagine. There was 48 Wiener with the definition of cybernetics, 58 Kalman with this rank condition for finite-dimensional system, 88 Lyons with his key observation that everything reduces to proving inequalities, and that this idea can be borrowed to understand properly the control of infinite-dimensional systems like PDEs, wave equations, heat equations, and also for doing numerical analysis of these problems. And since then, in the last 36 years, a huge amount of literature and very interesting mathematics have been developed for tackling these problems. In the next 2 or 3 lectures, I will present some of the progress that has been done on the understanding of these PDE-related and numerics-related control problems, to later, by the end of this series, go back to the problem of machine learning and try to explain you how and why we should now try to use all this know-how we have accumulated for tackling the challenges in artificial intelligence and machine learning. Thank you for your attention.
Thank you a lot, Enrique. This was a wonderful lecture today. Are there any questions online? So we have a couple of minutes, so please.
There is one question. Or is it a comment by Rod and David? I can see the Fredholm alternative relevant in some parts of the discussion. Any comment, Enrique?
Well, yes, of course. Let me see. How could I explain it? Yes, so it's a matter of kernels, right? So very often, let me see what is the simplest way of seeing Fredholm alternative? So what does the Fredholm alternative say? So it says that a system, yeah. So maybe that's a very good point. So maybe you have something else in mind, but let me get back to this point. What is it? No, it's here. Yeah, so that's a very good question, actually. So when the rank is n, it means by duality that the kernel of the adjoint is 0. So I have the unique continuation. So I have the observability inequality. Then I can build a functional J that by minimization leads to the optimal control. And this even leads to computational methods for doing this. But now the question is, what happens if you are unlucky and when you compute this rank, for instance here, right? When you compute this rank, it turns out that the rank here is n-1. What happens then? Then, well, this is telling you, listen, you are missing one direction. So what the rank being n-1 will mean is that you can almost achieve the controllability of your system. But unfortunately, out of the n dimensions of the system, one of them will not be controllable. Like, as I said, the car in space. I can move on the plane freely, but please don't ask me to do it vertically. For this, I need an helicopter, not a classical automotive car. So now, in general, of course, when you compute the rank and you see that it's n-1, you will know that you are missing one direction, but you will not know which one, you are missing. And this is where the Fredholm alternative comes to say, listen, the functional here, right? The functional here, I have written here, this functional will be coercive, right? For many of the targets, but not for those that are pointing in the wrong directions. So the Euler-Lagrange equation associated to the minimization of these functionals will have solutions only when the target, the destination, right, has fulfilled some compatibility condition. And this is precisely what you see in the Fredholm alternative, right? So if, the rank is not full, you can only expect the system to be solvable when the right-hand side is orthogonal to the kernel of the matrix, right? And this is what you will see by this duality technique. This duality technique will tell you, listen, if you want to understand what is the uncontrollable component, because once you know which is the uncontrollable component, you will focus on those that are controllable, and then you will succeed with those. If you want to understand which are the uncontrollable components, you have to look to the kernel of the adjoint, and whatever non-trivial you find in that kernel will be precisely one of these uncontrollable components of the system. So you are totally right. Fredholm alternatives, both in finite and infinite dimensions, will appear, especially as soon as the system is not controllable and you have to split the controllable part and the uncontrollable part. Because, of course, even when the system is not controllable, we still want to control well the controllable part. This is like when you are doing an exam, you have 5 questions, you say, oh, the 5th one, no clue. I didn't read, I didn't study the chapter, so I cannot do the 5th one. But let me focus on doing the first 4 perfectly, and then I will get 8 out of 10, or in France, 16 out of 20.
Thank you. So I think there are 2 other questions that we can address now before we stop. So the first one is, could those ideas be generalized to the case of fractional dynamical systems?
Fractionals in space, yes. So, I mean, if you replace a Laplacian by a fractional Laplacian, I mean, things are tricky, but this is more easy to understand. If you do it fractionally in time, this is more complicated, because fractional in time is like memory problems. And over there, even what controllability means is much more tricky to be understood, right? Because the system does not behave, right? So it's like, if I could give you this system already, which is simpler than a fractional ODE, right? And now, understanding what controllability means for this system is already more complicated, right? Why? Because there is memory. So even if you, at a given time, the state X get to the correct destination, this doesn't mean anything, because the memory is acting like a win, and maybe you will quit this destination. So if you want to guarantee that the system has reached an equilibrium, you have to rethink what equilibrium means. And actually, in this case, this is very easy to see, because if I take one more derivative of the system, this is what I get. I call u prime equal v. And now you see that, dealing with the control of the memory-like system is, in fact, controlling a system of a higher dimension. And therefore, I have to enrich the condition of control. So as soon, the short answer is, there is plenty to be done for fractional in-time systems. Why? Because as soon as there is some integral in time on the system, on the dynamics of the system, even the concept of equilibrium, and therefore reaching equilibrium, has to be rethought.
Okay, thank you. And another question by Nourdine. Is there an alternative to Kalman rank condition when this is not satisfied? So you can find it on the chat at one.
Well, so to me, this is also very much related to the previous question, right? Of Fredholm. I mean, to me, I like to think this way. So you give me a system, you can talk about control and the Kalman rank condition, but to me, all this means simply that an inequality like this is fulfilled. Now you tell me, what happens when the Kalman rank condition is not fulfilled? Well, I tell you, well, if the Kalman rank condition is not fulfilled, it means that this inequality is not fulfilled. Then basically there are 2 options, right? One of them, as indicated in the Fredholm alternative, well, what Fredholm is telling you, think, given that, maybe this is not true for all solutions, please give me the subclass of solutions where this condition is fulfilled. This is what Fredholm will tell you. And the other remedy, maybe more from a practical perspective, more useful, will be to say, listen, you say that this is not true, right? Oh, something is missing. Well, something is missing. So then add whatever is missing to make the inequality true. So an example, Poincare inequality. We are always so happy to have Poincare, right? So Poincare inequality says, Poincare inequality says that the integral of phi squared is less than c times the integral of gradient phi squared, right? For all phi in H1 omega. Is this true? Is this true? Poincare inequality, is it true? I think I'm forgetting something, right? Maybe I need more coffee. Yeah, I forgot that there should be a 0 here. Yeah, of course, Poincare inequality is true in the subspace H10. Now, I ask you, is Poincare inequality true in H1? And you tell me no, because the constant is a counterexample to this. Then there are two solutions. One will be Fredholm, to say, listen, you wanted this inequality in H1. I'm sorry to tell you that this is not fulfilled in H1. As a counterpart, I can tell you that this is true in H10. Or you can do a different thing. You can say, listen, this inequality in H1 is not true, but you know, I will add a small reminder and I will make it true. So Poincare-Wirtinger. You say, listen, the only impediment for that inequality to be true was phi to be a constant. So how do you take into consideration the fact that phi constant was an impediment for that to be true? Well, you needed to add the projection over the constants. And now the inequality is true. So this, you can do it also at the level of observability here for general systems. And what is the message you learn? Well, whenever a system is not controllable, you can either use Fredholm to confine yourself to the data that are controllable, or you can just figure out through a careful analysis of what is missing, you can just figure out what extra control you will need to enter into the system so to make the system controllable.
Thank you. And there is a very, very last one on the chat. Can you see it, Enrique? So partial time feedback control is important to consider in the case of switching, not only the maximum, as you explained, isn't it?
Well, partial time feedback control, this reminds me a lot to model predictive control. This is a very interesting idea. So, of course, there is a huge gap between open loop and closed loop, right? So in open loop, right, I am computing patiently the whole evening at home before I apply the control on the system, and you are not happy because it's taking too long. Now we went to the other extreme, and you said, oh, I want the control to be feedback. Yes, but this only Messi can do it. So there are semi-feedback controls, and this is what the model predictive control does. It's trying to make it feedback, but not completely feedback. So you refresh your control every, say, few time instances, right? And this is what the model predictive control does. And this is, so what about the random dynamic problem? Yeah. So precisely, model predictive control was aimed to tackle the two issues simultaneously, in some sense. Why? Because, for instance, think that all these mathematics, Pontryagin and so on, were developed when the humans were aiming to get to the moon, right? And there, the trajectories of the rocket are very long. You can compute offline in your laboratory the optimal trajectory before the rocket is launched. But of course, you cannot expect that your rocket will evolve exactly along the trajectory that you have anticipated according to your mathematical formulas. So you have to take measurements from time to time and correct the location of the rocket and recompute what the control should be. This is actually what we do. Humans, again, we are doing that spontaneously. We don't need to do mathematics or control theory to know that this is what we should do. You know, you take your Google Maps, you have to go from, you know, I don't know, from Nice campus to Sofia Antipolis, Inria, from the math laboratory to the Inria campus. You have to go by bike. You open the Google Maps and you see what the path is. But after 1 kilometer or so, you double check. Why? Because if you are new in the city, right, after a while, you don't know exactly whether you are following the optimal path indicated by the Google Maps. So you better check again and eventually recompute. In this way, you will do a path that is not optimal in the sense of Bellman, but it will be nearly optimal. But in order to do this, what you do is you compute the optimal path offline for a long time interval, and you apply it in a short time interval. And this allows you also, for instance, for unexpected events along the trajectory. For instance, a street that is broken, I mean, that is closed. Yeah, maybe Google Maps didn't anticipate that, right? But it turns out that the metro is not working today. So you have to take a different action. So model predictive control is always a good recommendation to be implemented because it can allow to handle with model inaccuracies, with numerical errors you introduce when computing the optimal controls, and it's getting you closer to the idea of feedback, knowing that pure feedback is hard to achieve because, you know, only Messi can do it.
Thank you. I think we should stop here. I think you need to keep some energy for tomorrow and for Thursday. So I think this is a good time to stop. Thank you again, Enrique. There are plenty of congratulations on the chat. I think that all of us really enjoyed. So we will meet again at the same time tomorrow morning at 10 a.m. French time and 9 a.m. Morocco time.
Yeah.
Okay.
Yes.
Very good.
Thank you, Enrique.
So, à demain. Merci.
À demain.
Bye bye.
À demain.
See you. Tschüss.
Bye bye.
Bye.